frozen reaches of Sweden, a team of scientists is drilling deep into solid granite in search of a precious substance, methane. Juvenile methane, they believe, was present during the formation of the planet, long before life evolved on Earth. These scientists are betting on a deep Earth origin of methane, unlike these petrofossil hunters who probe sedimentary rock. Whatever theory prevails, biological origin versus non-biological, it is known that petroleum contains over 500 naturally occurring compounds. But what accounts for this remarkable diversity? Again, the key is carbon's adventurous bonding arrangements. Take C4H10. There are two different structural formulas that can be derived from this one molecular formula. And these derivatives are called structural isomers. We'll now convert these formulas into ball and stick models. These two structures are N-butane and isobutane. Let's lose the hydrogens. Now we can focus on the alignment of the carbon bonds. The carbon spine of N-butane is called a straight chain, while the bonding arrangement of isobutane is called a branched chain. However, a hydrocarbon with the formula C5H12 has three different structural isomers, so that what stands out is a straight chain, a branched chain, and yet another different branched chain. The isomers are distinct compounds with different boiling points. Pentane boils at 36 degrees. 2-methylbutane at 30 degrees. And 2,2-dimethylpropane at 9 degrees. Now, if the number of carbon atoms is increased to 6, a total of 5 different chain structures are possible. Furthermore, carbon also forms ring structures. A 6-membered, a 5-membered ring with 1 carbon attached, or a 4-membered ring with 2 carbons attached, oriented in at least 4 different ways. If you're beginning to sense that you're staring at an infinite number of possibilities, you're right. But let's come down to earth and see how industry prepares hydrocarbons for fuels. The small hydrocarbons, numbering up to 5 carbons, make up natural gas. Of the organic portion of natural gas, methane constitutes from 60 to 95%. While the balance is composed of ethane and propane. But natural gas also contains inorganic impurities, useful ones such as hydrogen sulfide, and a downright nuisance, water vapor. The trick with this gaseous cocktail is to separate what we need. Water, which forms hydrates and clogs pipes, must be removed, so the gas is compressed at ambient temperatures, and water is drawn off in a liquid state. Now, because hydrogen sulfide is a weak acid, it can be removed by absorption in a weak base such as monoethanolamine. Eventually, this salt is converted into sulfuric acid or elemental sulfur. The dried gas is then cooled to minus 45 degrees Celsius in order to condense out most of the hydrocarbons of higher mass. Methane is then piped into factories and homes, where it makes an excellent fuel. Crude oil, on the other hand, is a complex soup, and the generic term petroleum refers to that part of crude that contains hydrocarbons of intermediate length. These are the volatile fuels, which have specific domestic and industrial applications. As the number of carbons in a chain increases, so does the boiling point. Because the boiling point range for each product is different, hydrocarbons can be separated by a process called fractional distillation. So, as you may have already guessed, the first step in the separation involves boiling the crude stock. The crude is zapped with superheated steam, and the vaporized mixture enters the fractionating column, where the temperature decreases from the bottom up. The vapors then begin to condense as they pass upwards through a series of horizontal trays and bubble caps. Vapor containing heavier molecules, namely those with higher boiling points, condenses in the lower trays, while the lighter molecules, or those with lower boiling points, proceed to the next layer of trays. Note that when the liquid fills the tray, it overflows back down to the tray below, so that revaporization takes place numerous times to ensure a more refined separation. Finally, the liquid fuels at target boiling points are continuously drawn off. Whether petroleum made the car industry or the car the petroleum industry, from decade to decade the consumer demands a different fraction from a barrel of crude. In the 1920s, the motorist got only 25% of a barrel of crude as gasoline. Currently, about 40% is needed, a proportion considerably larger than available through fractional distillation. So, chemical engineers reach down deeper into a barrel of crude to draw off the heavier hydrocarbons, those in the C30 to C40 range, and shunt them into a catalytic cracker where they are broken down into smaller hydrocarbons. A catalytic cracker consists of a reactor, a regenerator, and a still. The heavy oil stock is vaporized, mixed with a catalyst, and sent to a reactor where the actual breaking down and reforming of molecules occurs. The catalyst is recycled from the reactor to the regenerator, where the particles are cleaned by burning off the carbonaceous coating. In the reactor, the catalysts help to cleave long-chained hydrocarbons into groups of short-chained isomers. The cracked mixture now enters the still, where it is separated into high boiling point components, which are recycled for further cracking, and low boiling point components, namely gasoline and refinery gases. In this manner, the petroleum industry continues to satisfy the changing demands of the consumer.